Now, question number 8 says, explain the process to determine possible rational zeros of 2x cubed plus 17x squared plus 23x minus 21. So, we're going to be finding the possible rational zeros. So let's write down what we're going to be looking for. Possible So when we're talking about the possible rational zeros, we must remember a little equation that's going to help us figure it out. The equation has p plus or minus p divided by plus or minus q. So let's first write down the equation or the function that we were given. We were given 2x cubed plus 17x squared plus 23x minus 21. So now with the p and the q, we're going to see which one's which. So p will always be the last part of the equation. So this right here is p. And q will always be the beginning of the equation. So this right here is q. But when you use the equation, you have to put p over q. So we already have which one's p and which one is q. Now we have to see what the factors of p and q are. So let's find the factors of p first. The factors of p, and you always have to put plus or minus on each number. So let's go in order. 1 plus or minus 1 times what is negative 21 times plus or minus 21. 2 doesn't go into 21. 3 goes into 21. Plus or minus 3 and plus or minus 7. 4 doesn't go into 21. 5 doesn't go into 21. 6 doesn't go into 21. Well, 7 goes into 21 times 3. We already have that. And that's pretty much it for the factors of p. So now let's find the factors of q. So the factors of q, let's write that out. Well, our q is a 2, so plus or minus 1 times, and plus or minus 2, because only 2 times 1 gives you 2, or 1 times 1, which is the same thing. So now since we have our p and our q, we're going to divide. P is always on top. Always on top. So let's put p on top. Plus or minus 1, plus or minus 3, plus or minus 7, and plus or minus 21. Over plus or minus 1 and plus or minus 2. So we just took p, placed it on top, and we took q, placed it on the bottom. So now we're going to divide. We divide by everything. So we divide by everything by 1, and we divide everything by 2. So let's go ahead and do that. So 1 divided by 1, that's 1. So we get plus or minus 1. 3 divided by 1, that's 3. So we get plus or minus 3. 7 divided by 1, that's 7. So we get plus or minus 7. 21 divided by 1, that's 21. So we get plus or minus 21. Now we divide everything by 2. 1 divided by 2, that's 1/2, so plus or minus 1/2. 3 divided by 2, that's plus or minus 3/2. 7 divided by 2, that's plus or minus 7 divided by 2. And 21 divided by 2, that's plus or minus 21/2. So once we divided everything, this is what we get. We get plus or minus 1, plus or minus 3, plus or minus 7, plus or minus 21, plus or minus 1/2, plus or minus 3/2, plus or minus 7/2, and plus or minus 21/2. And those are your possible rational zeros. All of this right here, these are your possible rational zeros. Once again, we got this by taking the equation plus or minus p over plus or minus q. Remember that p is always the last term on the function and q is always the first term on the function. And then you find the factors of p and you find the factors of q, which in this case for p is 1 and 21, 3 and 7, and for q it's 1 and 2. And then you place p on top, and q on the bottom. You divide everything by the first number, and you divide everything by the second number. And that's how you got your zeros. So these are your possible rational zeros. Once again, we found that by having p over q. So now let's look at question number 9. How is a removable discontinuity determined? So let's look at that. So let's just write down that we are looking for removable discontinuity. Well, for starters, a removable discontinuity just simply means that the function is continuous everywhere except for a whole. So if we take the example x is equal to c, we see that when we draw a graph, where y equals f of x, we have the point C, and we just draw it, and right where it crosses it, there's like a little opening hole. This right here is the removable discontinuity. That right there is a removable discontinuity. So I just wanted to go ahead and show it this way so that you can see what it looks like. So it's where the function is continuous everywhere except for a whole, where it just continues and keeps on going until like it gets to a little hole and it has an opening. That's when it's removable discontinuity.